So just substitute this E value here. So sigma by 2 epsilon naught, then integral of constant, means its value is a constant, so I am writing outside. Then integral of dx you will get. So integral of dx is nothing but x you will get. So x minus infinity. So that means that results as infinity. That potential at that point is infinity. So which indicates that this is now similar to that of line of charge. So in case of line of charge, we discussed already. If you are taking the reference at say infinity, then potential at a point is not defined, right? So similarly here in case of this plane of charge also, if you are taking the potential at infinity as a reference, then potential at that point is not defined. Again, you will get that infinity. So instead of that, so we are using that means we can define the potential difference between 2 points similar to that of our line of charge. Or if a potential at a point is given to us, then we can calculate the potential at the other point. Now suppose here I am taking a condition like potential at the plane of this conductor is plane of this charge is V naught. I am assuming here, that means potential is V is equal to V naught when x is equal to 0. Then just here change the limits here. So instead of taking this infinity, now we'll take that x value is 0, then potential value is V naught. So just I am taking this potential limit, that means I am changing the limits in this step here. So then V minus V naught is equal to, same you will get, minus sigma by 2 epsilon naught. So instead of this infinity here, we need to write this 0. Then V is equal to V naught minus sigma x by 2 epsilon naught we can write here. So that means now instead of this, we can also use this EV relation also. That means we know, because the plane field produced by this infinite conducting plane is a uniform field. We know that it is independent of distance. And so when it is independent of distance, we can use this potential difference delta V is equal to E into D we can write here, right? And so now that is nothing but potential difference here. When you are writing like this, we need to write delta V as higher minus lower potential we need to write. So higher potential and lower potential, how to identify means, we know the point when you are traveling in the direction of field, potential goes on decreasing. So field is away from this plane, so potential V naught should be greater than that of this V. So here you can write this as V naught minus V. That means if you want to write it directly, you can write this as V naught minus V is equal to sigma into x by 2 epsilon naught you can write here. So directly if you want to write without using that integration, then from this V value we can write, then you will get the same expression here. So like this also you can solve, or by integration EV relation also we can solve here. That is in case of non-conducting. So this non-conducting under the, and that means the infinite plane of charge and the infinite line of charge, both are similar only. By taking potential at infinity, we can't define the potential at any other points. So we can define the potential difference between 2 points, or if your potential at a point is known to us, then we can calculate the potential at the other point there. So that you should remember. And next year there will be some problems, in simple problems will be there, like when bubbles, or that means like drops are combining with each other, then resulting potential we need to write here. Like suppose there are certain charged bubbles are there, so just write it as a note. So now here let us see n identical drops are having some charge q on each other, and so they are combining with each other. Suppose say here these small liquid drops are there here, and they are carrying some charge q on each. Such a large n number of drops are there. And so now such a drops are collapsed to form a big drop of radius r. And in such a type of problems, similar problems we solved in surface tension topic, like a drop is combining, that means it is dividing into droplets, or small droplets are combining into big drop. So such a problems we solved already. And so in that we can write the relation as, that means simply we can write, to write the relation between the smaller and capital R, we can consider this volume of this big drop is equal to, we can write this as volume of this n droplet. So by using that we can write this relation as this capital R is equal to n power 1 by 3 into small r we can write here. This relation between smaller and capital R. And so now potential of this small drop we can write it as this is potential I am writing here. So it is potential of small drop. So potential of this small drop, we can write it as, I'm taking it as some Vs, potential of small drop. So we can write simply it as KQ by R, potential of this small drop. Now such a big n drops are combining with each other, then total charge on the big drop we can write as, that means now potential of the big drop we can write as, so now it is potential of big drop. So potential of this big drop we can write it as K into capital Q by R we need to write. And now we can substitute this where capital K is the total charge. So by conservation of charge we can write this when n drops are combining with each other, then this total charge we can write as n into Q, right? And this radius relation we mentioned already here, so that we can mention it as n power 1 by 3 into R, smaller. Therefore this potential of this big drop we can write it as n power, so this is 1 by 3 here, so n power n by n power 1 by 3 means we can write this as n power 2 by 3 into kq by small r we can write. Now this kq by small r is nothing but potential on this small drop here. So we can write this relation as potential of this big drop is equal to n power 2 by 3 into potential of this small drop we can write here. So this is a relation between potential on the big drop and potential on the small drop. So just if you know the number of drops they are combining, then we can write that relation easily here. So this will be simple problems will be there basing on this. I think you can solve those problems easily. So next we need to discuss some problems based on this. So based on these problems, in the sense I can explain that in the next class. So you can solve the problems based on this level 1 and level 2 problems based on such a potential expressions and potential due to the continuous order distribution, or like this potential due to the drops problem. Such a problems you can easily solve. So in the next class we will discuss some problems based on the continuous order distribution, that means potential due to the continuous order distribution and their applications. And actually this regarding this spherical shells on the solid, that means solid sphere charge distributions, there will be a lot of problems will be there, and all those problems I will explain, like a potential concentric combination of concentric cells and generator problems, Van de Graaff generator we need to discuss. All those problems I will explain after the completion of Gauss laws, because once if the Gauss law is completed, then you can easily solve the concentric shells problems and the problems based on the induced charges, and all those problems we will discuss after the completion of this Gauss law here. Now in this week you need to solve just the direct applications of the potential due to the continuous charge distributions, continuous charge distribution, and potential due to the point charge distribution, and potential energy related sums there. So in the next class I will explain about those problems based on this continuous charge distribution and the conservation of energies with the continuous charge distribution problems.